Yo, what's up everyone? Welcome to States of Matter Part 3. Today we're going to be talking about kinetic molecular theory. In the last part, we talked about how ideal gases are going to follow the ideal gas law. And we use the ideal gas law even for real gases. But real gases are going to derivate from ideal gases. And if you wanted evidence of that, you could look at this. So at STP, standard temperature and pressure, which is 0 degrees Celsius and 1 atmosphere, the molar volume of an ideal gas is 22.4 liters. So an ideal gas, 1 mole of it is going to occupy 22.4 liters. If you looked at real gas data though, you could see that at one mole, they're going to take up different volumes. You can see something like oxygen takes up 22.4, but something like ammonia is going to take up 22.1-ish. So real gases do derivate from ideal gases. So what makes an ideal gas? Well, we use something known as kinetic molecular theory as a model to explain properties of these ideal gases. So gases that follow these properties are assumed to be an ideal gas. And there's going to be like 5 little postulates. The first one is the fact that the volume of individual gas particles is assumed to be 0. If you looked at a real gas particle, it would of course have a volume, but it's so small and nearly negligible that we assume it to be 0. The second one is the fact that the particles are in constant motion. Pressure is caused by the collisions between the gas and the walls. This is what's creating pressure, and so these particles are always in motion. There's not a moment of time where they're kind of stopping. 3, collisions between particles is elastic. Now, the fact that they're elastic means as the particles collide with each other, they're going to rebound with the same energy. They don't ever lose any energy in collisions. So that's how these particles are constantly staying in motion, because they never lose energy when they collide. 4, the particles neither attract nor repel each other. What this means is that we don't have any intermolecular forces. If you look at a real gas, of course you would have intermolecular forces, but under kinetic molecular theory, we assume no intermolecular forces to make talking about ideal gases a lot easier. 5, average kinetic energy is proportional to the Kelvin temperature of the gas. And I want to go a bit more in depth into this one. So average kinetic energy is proportional to Kelvin temperature of the gas. And this makes sense. If you increase the temperature, what you're doing is you're increasing how fast the particles are moving. And if you increase how fast the particles are moving, they're going to have a higher average kinetic energy. And we actually have a formula to show this. We have that the average kinetic energy is equal to 3/2 times R times T. So R is the gas constant, and in this case, considering our units, we want to use 8.3145 joules per moles times Kelvin. T is the temperature in Kelvin. Now remember, Kelvin is going to equal 273 plus the degree Celsius measurement. So that's how you convert from Celsius to Kelvin. Let's do like a little example. What is the average kinetic energy of a sample of helium gas at 33 degrees Celsius? Well, average kinetic energy is going to equal 3/2 RT. So that's going to be 3/2 times 8.3145 joules per mole times Kelvin times the temperature. So we're given 33 degrees Celsius. So we need to add 273 to get 303 Kelvin. So we multiply by 303 Kelvin, and this gets you a final answer of 3816.4 joules per mole. And there's 2 things to notice about our answer. First of all, we had the fact that it was a sample of helium gas had nothing to do with our answer. The gas itself is not going to have an impact on the average kinetic energy, and this comes from the fact that we're using the kinetic molecular theory. And in kinetic molecular theory, we don't have any intermolecular forces. We kind of just assume their volumes to be 0, so there's really not a lot to differentiate between different gases. So that's the first thing, the fact that the gas itself doesn't really matter. And the second bit is the fact that our units is joules per mole. The fact that it's joules per mole tells us that we're dealing with energy. But sometimes you don't want to know energy. You want to know how fast are the particles moving. You want to know their speed. And for that, you would use root mean square velocity. So the root mean square velocity is the velocity of the particles, the average velocity of the particles, and it's equal to the square root of 3 times RT over m. M is the molar mass in kilograms. Be careful about that, it's in kilograms. So let's do an example. What is the root mean square velocity of a sample of hydrogen gas at 100 degrees Celsius? So the root mean square velocity is equal to the square root of 3RT over m. So the square root of 3 times 8.3145 joules per mole times Kelvin times the temperature. We have 100 degrees Celsius, so that's 373 Kelvin. And all of this is over the molar mass in kilograms. So we're dealing with hydrogen gas. Hydrogen gas is H2. Remember, hydrogen is one of your diatomic elements. So your molar mass is 0.002 kilograms. And if you did all the math out for this, your root mean square velocity would come out to 2156.8 meters per second. So this gas particle is moving pretty fast. And so that's the difference between your average kinetic energy and your root mean square velocity. One of them has the units of joules per mole, so we're dealing with energy, and the other one has a unit of meters per second, so we're talking about velocity, or we're talking about speed. And so let's do an example of a problem using kinetic molecular theory. The kinetic theory of gases assumes all of the following except A, gases are composed of particles in random ceaseless motion. That is one of the things that we talked about. These particles are always moving, and their collisions are elastic, so they don't really lose energy. They're always in motion. B, the size of gas particles are negligible compared to the size of the container. This was postulate 1. We assumed that the volume of the individual gas particles is assumed to be 0. Now, so it can't be B. C, gas particles do not attract or repel each other. This is what we talked about. They don't attract nor repel, so their intermolecular forces are basically none. And so it must be D. When gas particles collide, kinetic energy is lost. Remember, their collisions are elastic, meaning that when they collide, they don't lose any energy. The energy that they came in with is the energy that they leave with. So they don't lose energy under kinetic molecular theory. So our answer is D. And that's it for kinetic molecular theory. I hope you were able to learn something. If you have a question, please feel free to leave a comment. And thank you for watching.